Hello guys, welcome back to my channel and let's do some math for fun. Let's get started. So like most of the times we have a problem. Let's call it I, defined as integral from 0 to infinity of the natural log of 1 plus x cubed divided by x cubed dx. So before doing anything, I would like to point out that this video is going to be all about um, complex analysis and contour integration. But if you're saying that we take this function for contour integration, then you're mistaken, because the only singularity you have is at 0. And if you want to remove that, that's not going to turn out really well. The residue is not going to turn out really well. I think it's going to go to 0, the residue. And it's a really bad place to work with, a singularity of 0. So what I'm going to do is I'm going to basically integrate this while I differentiate this using integration by parts. So integral of this of x to the minus 3 is just going to be x to the minus 2 divided by 2. So we have half of natural log of 1 plus x cubed as it is divided by x squared evaluated from 0 to infinity minus derivative of this is integral from 0 to infinity 3x squared divided by 1 plus x cubed times this original x squared dx. The best part, both of them will cancel out, giving us half of natural log of 1 plus x cubed divided by x squared evaluated from 0 to infinity. That's the first part. And then we have, well guys, I forgot to take this minus into account, so I'll just do that. We have minus over here, and minus minus plus 3 over 2 times integral from 0 to infinity of dx over 1 plus x cubed. Now the challenge here is tackling this function at infinity and 0. So I'm going to just do that quickly. So we have limit as x tends to infinity of natural log of 1 plus x cubed divided by x squared. Notice if you plug in infinity, the natural log of infinity is infinity and infinity in the denominator. So infinity over infinity sounds like it's a job for L'Hopital's rule. So applying that, we just have the same limit as x tends to infinity. But now we differentiate the numerator. We have 3x squared divided by 1 plus x cubed divided by derivative of this is 2x. Cancel the x's if you want. Limit as x goes to infinity of x over 1 plus x cubed. Again, infinity over infinity. L'Hopital rule once again. Limit as x goes to infinity of 1 over 3x squared, and as x goes to infinity, the denominator will grow way faster than the numerator, which is constant. So this entire fraction will go to 0. So at infinity, this goes to 0. What about 0? So limit as x tends to 0 of natural log of 1 plus x cubed divided by x squared. If you plug in 0 here, we have natural log of 1, which is 0, and 0 in the denominator also. 0 over 0 situation. Again, time for L'Hopital's rule. Limit as x goes to 0, and the derivative of this will just turn out to be this, right? We just calculated the same derivative, x over 1 plus x cubed. But we don't need to do L'Hopital's rule again, because if you plug in 0, we have 0 over 1 plus 0, which is 1. So 0 over 1 is 0. So at both infinity and 0, this turns out to be 0. So entirely this is 0. So for calculating I, all we have to do is look at this part, which is 3 over 2 times integral from 0 to infinity of dx over 1 plus x cubed. Now strictly speaking, there is actually no need to use complex analysis to calculate this integral. We can use partial fraction decomposition by splitting 1 plus x cubed as 1 plus x times x squared minus x plus 1, basic algebraic identity, and then use partial fraction decomposition, and then we obtain natural log expressions and stuff, and when we can calculate 0 to infinity in that. But it's still going to be quite cumbersome. So let's be fancy and use a complex analysis or residue theorem or contour integration, whatever you want to call it. So if we have to integrate a function that looks like this, let's generalize it, make it a complex function f of z defined as 1 over 1 plus z cubed. Okay, and now let's draw the contour. So our contour essentially looks like this, and notice it's quite weird. It's not a regular semicircle that we have, and I'll explain the reason for this briefly. So all you need to know is this is the real axis, this is the imaginary axis on the complex plane, and this subtends an angle of 2 pi over 3 radians with respect to the real axis, this segment. So the way we are going to do this is we're going to go from 0 to this point which we call R, and then we go across this path, let's call it small gamma, and then when we reach this point, which is again at a distance R from this origin, we move down from that R to 0 on this path, let's call it alpha, and you can say this path is beta. So our entire contour integral of f of z with respect to z is going to look like, in segments. So integral over beta of f of z dz plus integral over small gamma of f of z dz plus integral over alpha of f of z dz. And what we are going to do is we are going to parameterize each of the paths, and while doing that you'll know the reason for subtending an angle of 2 pi over 3 and not pi radians like we always do. So integral over beta, the parameterization that we do is we let z equal to x, because there is no y component, there is no imaginary component, because traditionally z is defined as x plus iy, but being on the real axis from 0 to r on path beta, the imaginary component is 0. So we can parameterize beta as being integral from 0 to r of z equals x. So f of z will be 1 over z cubed, but z is equal to x, so 1 over x squared, or x cubed, sorry, 1 plus 1 over x cubed. And dz will be dx, naturally, because dz is equal to dx. We'll write integral over gamma as it is for now. And integral over alpha, or this path. Well, how do we represent points on alpha? What parameterization we use? Well, notice that every point on path alpha is actually a rotation of a point on beta by 2 pi over 3. So this point here, say z2, when rotated by 2 pi over 3 ends up on z sub 2 beta. And the way to do that is to have x, because that's what the parameterization for beta was, no imaginary components, and multiplied by e to the I times what angle of rotation was occurring, 2 pi over 3. And you can check if the angle subtended was pi radians, which means we would have points here, so on the negative axis we would have x times e to the I pi, which is -1, so negative x, so that makes sense. This is a general way of representing points on alpha, and that's the parameterization we are going to use. So we're going to let z equal x times e to the I 2 pi over 3. When we do that, we have integral from r to 0, because we're going this way, So integral from r to 0 of 1 over 1 plus, instead of z cubed, we have x times e to the I pi, 2 pi over 3, the whole thing cubed, times dz is equal to dx times e to the I 2 pi over 3. So e to the I 2 pi over 3 dx. So we have integral from 0 to r of dx over 1 plus x cubed. I'm going to pull out a minus and flip the order of integration here. So integral from 0 to r now, minus e to the I 2 pi over 3 dx over, this will be x cubed, and e to the I 2 pi over 3 cubed is e to the I 2 pi over 3 times 3. The 3's will cancel out in the numerator and denominator, giving us e to the I 2 pi, which is 0 because e to the I theta is cosine theta plus I sine theta. When you let theta equal 2 pi, you have cosine 2 pi, which is 1, and sine 2 pi, which is 0. So you have 1. So 1x cubed will make it just 1 plus x cubed. Plus we still have integral over gamma of f of z dz. So now what I'm going to do is I'm going to club both of these integrals together. So we have 1 minus e to the I 2 pi over 3 as a common factor, and integral from 0 to r of dx over 1 plus x cubed plus integral over gamma of f of z dz. That's exactly what our contour integral of f of z dz is equal to. That's the contour equation, so as to put it. Fine, now let's look at this integral over gamma on a fresh page. See you there. So the integral over gamma is essentially going to look like this. I just substituted f of z later on. And now what I'm going to do is, since our gamma is something like this, basically a curved path like this, this is our gamma. I'm going to parameterize z to be r, because that's the radius, 0 to r times e to the it, where t goes from 0 to 2 pi over 3, right, because the final angle is 2 pi over 3. So we can make that substitution, giving us integral from 0 to 2 pi over 3 of dz is ri times e to the it dt. So ri times e to the it dt divided by 1 plus r cubed times e to the 3it in the denominator. So now what I'm going to do is I'm going to take basically the mod of this. So the mod of integral from 0 to 2 pi over 3 of ri times e to the it dt divided by 1 plus r cubed e to the 3it. We know that this is less than or equal to integral over from 0 to 2 pi over 3 of the mod of the integrand, which is mod of ri times e to the it times mod of dt divided by mod of 1 plus r cubed times e to the 3it. And now using the triangle inequality, we know that say mod of z1 plus z2 is always going to be greater than or equal to mod of z1 minus mod of z2. And when we take the inverse, the inequality switches. So this inequality can be again written is less than or equal to integral from 0 to 2 pi over 3 mod of this, mod of r is r, mod of I is 1, mod of e to the it is 1. So mod of r is r, no need for the mod because r is again going to be positive, dt is positive dt divided by, this is going to be mod of 1 minus mod of r cubed times e to the 3it. This is just going to be equal to integral from 0 to 2 pi over 3 of r dt divided by 1 minus mod of r cubed times e to the 3it. E to the 3it mod will be 1. We have 1 minus r cubed. And now what I'm going to do is I'm going to take the limit as r goes to infinity. So in the limit, integral from 0 to 2 pi over 3 of r over 1 minus r cubed dt will go to 0, because notice the denominator will grow faster being a cubic term. The numerator is linear. You can do L'Hopital's rule if you want, but denominator will go to infinity quicker, making the entire term go to 0. So this means that the mod of this, basically the entire expression, was less than or equal to 0. But since the mod is strictly positive or equal to 0, the only way that both of these conditions are satisfied is if this thing is equal to 0. So mod of something is equal to 0, which means that thing of which we took the mod has to be equal to 0. So that's why integral over gamma of f of z dz is equal to 0. So good riddance, right? One integral less to worry about. But before going on to residue theorem, I would like to explain why 2 pi over 3 was chosen. Notice the denominator has x cubed. So you choose an integral. So you choose a contour where the final path that from where you return to 0 subtends an angle of 2 pi over whatever power x was raised to. So if we had something like integral from 0 to infinity of dx over 1 plus x to the n, then the angle you would subtend on your contour is 2 pi over n. If you had something like integral from 0 to 2 pi of dx over 1 plus x to the fourth, angle you would subtend is 2 pi over 4, which indeed is pi over 2. So you'd subtend an angle of 90 degrees. Because the reason this trick is really useful is because when you consider this last path, that factor of e to the I 2 pi over 3 raised to in a general case 2 pi over n raised to an nth power will give you e to the I 2 pi, which is just 1. So you can write everything in terms of multiples of the original integral that you wanted to find out, and this makes stuff really easy for us. Because if in this case, if we had chosen a 180 degree rotation on the final path, we would have obtained on this integral from minus r to r 1 minus x cubed, right? Because minus x cubed is minus x cubed, and that would have been a real problem because 1 minus x cubed is not the same as 1 plus x cubed. So this is a neat trick. It's good if you remember it. So now to use residue theorem, we need the residues, and for residues we need the poles, or the points where the denominator is equal to 0 or f of z is basically undefined. So looking at the denominator, z cubed plus 1 is equal to 0, you might clearly just instantaneously say that one point is z is equal to minus 1. Well, you're not wrong, but thing is, we're dealing with complex numbers, so there have to be two other poles, because essentially this expression is cubic, so it has to have three solutions. Doesn't matter if they're complex or not. In this case, both of the other ones are complex. Only one of the solutions is real of minus 1. So in order to find those two solutions, what we do is we use the algebraic formula of z cubed plus 1 is basically z plus 1 times z squared minus z plus 1, and all of this is set to 0. Ignore this case because we found z equals negative 1 as one pole. We need to calculate this quadratic of z squared minus z plus 1 is equal to 0. Using the quadratic formula, we have z is equal to minus minus plus 1 plus minus square root of 1 minus 4 divided by 2, giving us two sets of values. Z1 is equal to 1 plus square root of 3i, where I is square root of negative 1 over 2, and z2 is just a complex conjugate of this, which is 1 minus square root 3i over 2. But the poles that we need to actually worry about in order to find the residues we need to find at those poles that are located inside the contour. So just briefly drawing the image of the contour, our contour was roughly something like this. So -1 is over here, it doesn't lie inside the contour, so just forget it. This can be written as half plus square root 3 over 2i, which if you want to write in terms of angles can be written as cosine of pi over 3 plus I times sine of pi over 3, which is equal to e to the I pi over 3. So which means this subtangent angle of pi over 3 with respect to the real axis, which is this. So which means this is somewhere over here. Z1 is somewhere over here, like that. And this subtangent angle of 300 degrees, so which is over here. And one interesting property of these three poles or solutions to this equation is that if you join both of all of these, three of these, they subtend an equilateral triangle. They subtend an equilateral triangle because this has a distance of 1 from the origin, and all of these other things have a radius of 1 and angle of pi over 3. So equilateral triangle. So that's one interesting property. So all we need to worry about is basically Z1, not even Z2. Forget Z2. We all need to care about Z1 now. So let's find the residue of that. So knowing all the poles, we can express our f of x now. I mean, it just doesn't matter what variable we are, x, z. 1 over 1 plus x cubed can be expressed in terms of product of these factors, and we want to find the residue at z1. So the way we are going to do this is basically have limit as z goes to z1 of x goes to z1, because it's an f of x minus z1 times f of x. So when we do that, we just have limit as x goes to z1 of this factor will cancel out, we're multiplying by that, 1 over x plus 1 times x minus z2, and when you plug in z1 in place of x, z1 minus z2, you can do this, z1 minus z2 is just going to be square root 3i. And yeah, let's just write it out. And z1 plus 1 is basically this plus 1, which will be 3 plus square root 3i over 2. So now we have 1 over square root 3i plus 3 over 2 times square root 3i. The 2 will go on top. We have 2 divided by 3 times square root 3i minus 3. We multiplied by this square root 3i everywhere inside. So we can basically factor out a 3. We have 2 over 3 times square root 3i minus 1. Let's multiply and divide by the complex conjugate of this, which is minus square root 3i minus 1, giving us basically 4 in the numerator, the denominator, and a minus we can plug out. So minus 2 over 3 times 4 and square root 3i plus 1. Finally, we have the sum of residues, because that's the only residue, is minus 1 over 6 times 1 plus square root 3i. But we know that the contour integral f of z dz is basically equal to 2 pi I times the sum of residues. So just multiply by 2 pi I. We have minus 2 pi over 6 times I squared is minus 1, so minus square root 3, which will just be minus pi over 3 times I minus square root of 3. But let's remember what our contour integral was. It was basically 1 minus e to the I 2 pi over 3 times integral from 0 to r of 1 over 1 plus x cubed dx. So if we took the limit as r tends to infinity for the lemma case, the gamma path, let's take the limit as r goes to infinity here. So r going to infinity, we have dx over 1 plus x cubed, which is nothing but I. So I is nothing but 1 minus e to the I 2 pi over 3 times minus pi over 3 I minus square root 3. So I can be written as, expanding this out, cosine of 2 pi over 3 is minus half. So 1 minus minus half is 3 over 2 plus square root 3 over 2i in the denominator now, because we're dividing both sides by that. So minus pi over 3 times I minus square root 3 divided by, the 2 will go on top from this, 3 minus, or rather plus square root 3i. It looks like that it's actually time to plug out it seems it's time to plug out a square root 3 from the denominator. So it's minus pi over 3 root 3 times basically this 2 that we had, and we have I minus root 3 divided by, we plugged out a root 3, so root 3 plus I. Take the negative to flip everything, so we have 2 pi over 3 root 3 square root 3 minus I divided by square root 3 plus I. Again multiply, divide by the conjugate of the denominator. So in the denominator this will become 4, so 2 pi over 3 root 3 times 4, and then root 3 minus 1, the whole thing squared is 3 minus 2 root 3 I minus I squared, which will be positive 1, so 3 plus 1 is 4. Finally we have 2 pi over 3 root 3, and the 4s will cancel for the real part, minus, we're left with over here, for the imaginary part we're left with I times pi over 3, and this is equal to I, which is defined as integral from 0 to infinity of dx over 1 plus x cubed. So, and since our I is real, so just ignore this part. A real integral over real number has to be real, it can't be imaginary, it makes no sense. So I is 2 pi over 3 root 3. But here's the catch, it's not exact, I wasn't exactly alone. I was actually 3 over 2 times whatever this thing was. And I made a mistake with the the alphabets. We should have called this I1 or something. So the result we obtained after everything is 3 over 2 times, after complex analysis of this, is 2 pi over 3 root 3. The 2's and the 3's will cancel out like this, giving us our final I is equal to pi over root 3. So this is just equal to pi over root 3, and that's a really nice way of calculating this integral. Now if you want, I can give you one integral for to try during your period of boredom. See, I sub 2 is equal to integral from 0 to infinity of natural log of 1 plus x to the 4 divided by 1 plus x squared dx. And spoiler alert, this is actually equal to pi over 2 times the natural log of 6 plus 4 times root 2. So can you prove it? Now it's become a question of proving. So you just try it if you have time. If you learned something from my videos. That's it for this video. So please like, share and subscribe to my channel. Recommend me to your friends, mathophiles, mathematicians, physicists, anybody, I don't care. I just want more support. Follow me on Instagram, gamma_digamma. And in the meantime, stay home, stay safe, have a great day and peace out.